This is a wind turbine, but so is this, and even this. So, which one is the best? That's exactly what we'll be discussing today. Why, out of all these designs, do we tend to choose the 3-blade horizontal axis? And what distinguishes it from the rest? Stay tuned, as today we're discussing the insane engineering of wind turbines. So, to really understand the root cause of this issue with blade design, we must talk a little about the Betz limit. You see, in practice, a wind turbine, regardless of its number of blades, cannot capture more than 59.3% of the energy from the incoming wind. This percentage is the maximum efficiency possible of any wind turbine, regardless of its shape and size. With this value in mind, engineers strive to design turbines as close as possible to the Betz limit. However, there are still some limitations that we cannot overcome, at least until now. The most common type of wind turbine, the 3-blade design, achieves 51% efficiency. You see, efficiency is heavily dependent on the blade's design. The power output of a wind turbine, meaning how much electricity it could generate, is directly proportional to the swept area. The swept area is the total area captured by the blades. The larger the blades, the more wind they capture, hence the more power they can produce. And the more blades we have, the more rotation force or torque is generated, and the slower the speed of the turbine. Although the one-blade design is considered theoretically the best, having the least drag due to it only having one blade, it is in most cases impractical because of the imbalance attributed to having a single blade. If we increase the number of blades, say 2, this creates a different problem. You see, an even number of blades present a different kind of imbalance because of the unavoidable problem that one blade always opposes another. Stability and vibrations are inevitable. The structure has to be more robust and heavier to accommodate the vibrations. As a result of vibrations and instability, the lifetime of components such as bearings, gears, and other drivetrain components is significantly shorter, leading to more frequent downtimes. This leads to the power output of these turbines to be relatively inconsistent if compared to the 3-blade design. Hence, an odd number of blades is preferred for balance, because as one blade is horizontal, its 2 resistances are balanced by the 2 other blades. Thus, the 3-blade design contributes the least stress on components and rotor vibrations. Turbines with odd number of blades are also the most consistent in poor wind conditions. Apart from this, for a 2-blade design to match the efficiency of a 3-blade design, it must rotate faster. A recent study has shown that 2-blade turbines are 3% less efficient than their 3-blade counterparts. In terms of weight and cost, 2-blade designs have a clear advantage with fewer manufacturing, handling, transportation, and assembly requirements, because there is one less blade to worry about. Studies have shown that 2-blade turbines cost 10 to 12% less than 3 blades, 30% lighter, which is advantageous especially for offshore applications. We have to consider that onshore turbines are sometimes installed close to habitable areas, so the noise and aesthetics have to be considered as well. 2-blade turbines have to rotate at higher speeds to maximize efficiency. When we increase the number of blades, the rotation speed is reduced, which reduces the noise levels. An interesting fact is that, according to a number of surveys and studies, we have also concluded that a 3-blade wind turbine is much more satisfying to look at as compared to a 1 or 2-blade design. A type of turbine which a large majority of us probably never encountered is the vertical axis turbine. The main difference is the axis of rotation, which is shifted by 90 degrees. They are used albeit far inferior to the 3-blade turbine, but still, we do occasionally install them in certain locations. They can be classified into two forms: the Savonius, which works by drag, and the Darius, which is powered by lift. If you don't know what lift and drag are, I explained that in a recent video I've made, which should appear somewhere. The Savonius turbine design is mainly installed in small-scale urban areas such as rooftops. However, the Darius turbine is used in utility-scale sites. Their main advantage is that they are installed closer to the ground than a horizontal axis turbine. Being closer to the ground is advantageous in areas with variable or inconsistent wind patterns. Because of this design feature, they could capture winds coming from virtually all directions, unlike the restricted horizontal axis turbines. Albeit, horizontal axis turbines are able to adjust the yaw angle to face the wind, but not with the same flexibility to vertical axis turbines. The main drawback of these turbines is the lower efficiency, ranging between 35 to 40%, which is significantly lower than conventional horizontal axis turbines. And being closer to the ground, they do miss out on consistent winds available at higher altitudes. The beauty of engineering is that there are little limitations to what we as engineers are able to design. I truly admire the creativity and ingenuity of these designs. To sum up this video, the main reason why the 3-blade design has come to dominate the market is a compromise between the lowest cost, a simple and reliable design, scalability, high power efficiency, weight, and being aesthetically pleasing. Guys, if you enjoyed this video, I recommend you watch this one next, where I explain key problems and innovations of wind turbines. Don't forget to like and subscribe, and I'll see you in the next one.